Okay, today we're going to start section 1.3. We're going to be talking about transformations. So we're going to look at a lot of commonly used parent functions and understand the transformations that can be applied to them. So you have the sheet in front of you for these common functions. I'm going to go through them relatively quickly. There's a few that I'll stop on because they may be new to you, or there's a few details I have to point out about them, but otherwise we're going to go through the common functions part kind of quickly. So first we have a linear function. This is the basic function right here. F of x equals x, has a slope of 1, y-intercept of 0. We should all be very familiar with that. Here we have the greatest integer function. So note this symbol here. This is not an absolute value with brackets around it. That's the greatest integer symbol. Now, one detail about this is a function. It's hard to tell from the picture. So there are closed circles at, for example, the points 0, 0, 1, 1, negative 1, negative 1, and so on. And so then there would be open circles at, for example, the point 1, 0, and 2, 1, and 0, negative 1, and so on. So that's where the open circles are versus the closed circles. So the domain is all real numbers. Then we have the Signum function. Again, it's a little bit difficult to see, but here there is a closed circle at the point 0, 0. And then there are open circles at the point 0, 1 and 0, negative 1. So again, domain is all real numbers from negative infinity to infinity. Quadratic function, this is f of x equals x squared. Cubic function, f of x equals x cubed. Absolute value function, f of x equals the absolute value of x. The inverse function, f of x equals 1 over x, has a horizontal asymptote at y equals 0, vertical asymptote at x equals 0. And then the last common function we're going to talk about is the square root function. So now take a minute and go through the back side of that page, the transformations, and try to describe what is happening in each transformation. So pause the video and then we'll go through those. Okay, so hopefully on this first one you recognize that it's shifted 2 to the left. So here I've drawn in what the original square root function looks like, but now we shifted 2 to the left because of the plus 2 within the square root. So this would be the same as if I said h of x equals the square root of x, then f of x equals h of x plus 2. So that's how we see that we're shifting 2 to the left. Hopefully on the next one you said that it shifted 2 down. And so again, here in red I've drawn the original square root function, which I'm calling h of x. So then f of x is h of x and then minus 2. So this is a vertical shift because the subtraction in this case is outside of the original function, which is the square root of x. Okay, this one's a little bit more difficult to see, but hopefully you did not say multiply the y or multiply the x values by 2. What this is actually doing is dividing the x values by 2. So in green here I've drawn the original function, and if I look at when x is 1, now it's 1/2. When x was 4, now it's 2. When x was 9, now it's 4.5. So I'm dividing the x values by 2, and then again, here's the relationship. If I say h of x equals square root of x, f of x is h of 2x. Okay, this one's a little bit easier to see. So here we're actually multiplying all of the y values by 2. So this is a vertical stretch. And I can see that here when the y value is 1, now it's 2. When the y value is 2, now it's 4. When the y value is 3, now it's 6. So my relationship is h of x equals the square root of x, f of x equals 2 times h of x. So again, this is a vertical stretch now. And I'm sorry, real quick, back to this last one here where we divided the x's by 2. This was a horizontal shrink, so I didn't specify that. Okay, this one, hopefully we understand that the 2x would divide the x's by 2, so since it's negative 2x, we're going to divide the x's by negative 2. This creates a reflection over the y-axis and the same horizontal shrink as before. So again, here in green, I've drawn the original function, h of x, and then f of x equals h of negative 2x. Okay, and then this last example, hopefully we recognize that we're going to multiply the y values by a negative 2. So what this does is this is going to reflect over the x-axis, and we are going to have the same vertical stretch we did when we had just multiply the y values by positive 2. So if h of x equals the square root of x, f of x equals negative 2 h of x. Okay, now I want you to pause the video and copy down or draw this graph here that I have on the coordinate plane. That is your f of x function, and I want you to perform the transformations up here to create the h of x function. So pause the graph, draw down the original, and then draw h of x. Okay, so this is what your result should look like. We are dividing the x by negative 2 and subtracting 3 from the y, or shift down 3. So that's how I got these points. So basically I started by looking at these points, or I can color code this a little bit better even, so I'll show you that. So this is at an x value of negative 4. So if I divide that by negative 2, that becomes positive 2. And then I shift down 3. So that's how I got this point. Here, this one, so let's make this purple instead. This is at an x value of negative 2, so negative 2 divided by negative 2 becomes positive 1. And then I shift down 3. So that's that point. This point here is at positive 2. So positive 2 divided by negative 2 becomes negative 1. Shift down 3. That's that point. Here I'm at positive 6. So if I divide that by negative 2, I'm at negative 3. And then I shift down 3. And then I connect the dots, and that's how I get my new function. Okay, now I want you to look at this function, f of x equals the absolute value of x plus 3 minus 4. I want you to describe how this is going to change compared to the standard or common function, h of x equals the absolute value of x. And then I want you to graph f of x as well. So pause the video and do that. Okay, so here I've graphed the f of x function in red, and the h of x function being the common function in purple. And hopefully we understand that this was a horizontal shift left 3 and a vertical shift down 4 from the common function. Okay, for our last example here, I want you to copy down this picture and then figure out or write down what is the common function, and then for this particular graph, what is the actual function. So pause the video and do that. Okay, so hopefully you figured out that f of x being the common function, or what I'm calling the common function, was x cubed, and then the actual function here, what I'm calling h of x, is the quantity x plus 1 cubed plus 2. So what happened? Well, we shifted left 1 and up 2. Or we had a horizontal shift left and a vertical shift up. Now, one thing you might ask yourself is, well, how do I know that there wasn't a stretch or a shrink in there? Well, I have to know some other points on the common function. And the 2 points that I focused on were this point and this point. So I know that from the center of the common function, if I go 1 to the right, I should go 1 up, unless there is some sort of stretch or shrink. And if I go 1 to the left, I should go 1 down, unless there is some sort of stretch or shrink. And so if I look at the center of my actual function, If I go 1 right, I go 1 up, and if I go 1 left, I go 1 down. So those 2 points are the points that are telling me that there was no actual shrink or stretch. So in conclusion, we want to understand translating or shifting of functions. Anything within the x affects the x value, and we do the opposite. So within the x, we're talking about inside the common function. Anything outside the x affects the y values, and it's not going to be the opposite. It's going to be whatever the operation is. And so again, what we're talking about with outside the x is we're talking about outside of the common function.